I'm going to review the formation process of all of these gas giants and the ice giants as well. And then I want to check out this paper that I found yesterday. I want to walk you guys through it a little bit because it illuminates, I think, some of the gaps in our understanding and possible solutions to them, which involve more of these migratory and catastrophic collisions and things that we traditionally have avoided in astrophysics. And then we're going to go through Uranus and Neptune, which are our two ice giants. So let's get started here. The traditional models that people used for the terrestrials are less debated right now. This idea that they can accrete from pebbles into planets is the modeling of that seems to be robust enough that it makes sense. There are some issues with it, and we talked about those. They can't really actually explain how something goes from being a pebble to a boulder. It's very easy to get boulders to turn into a planet, and it's very easy to get dust to turn into pebbles. But getting those two to come together is a huge gap in our understanding. But aside from that, and with respect to the gas giants, the formation is there's a lot less gaps in our understanding. When it comes to the gas giants, the basic idea is that, like the rocky planets, they form this core, which is pretty large, something like 10 Earth masses, which then begins to grab in a lot of the circumstellar gases and makes these it grabs these atmospheres up around it. And then over the course of a few millions of years, they're able to form something that looks like a planet out there. Again, Uranus, well, actually, we haven't talked about this yet. So Uranus and Neptune, and for that matter, these ice giants in general are thought to happen much in the same way. A small rocky core happens first. The story that we're moving away from, and the one that we should start with today, is that they form very far away from the interior. And so the molecules that are present out in the reaches of the solar system are volatiles, and they form ices. And these ices can nucleate much in the same way a gas giant would grab up a bunch of gas. These ones grab up a bunch of ice. Now, there's been recently some serious problems with this model, because what happens is if you crunch the numbers and you try to make one of these ice giants out at that region, which is about somewhere like in the icy region, about 20 astronomical units, so 20 times the distance that we are to the sun. The problem is they move too slowly at that distance to stay in orbit, right? So their escape velocity is about the same as their forward velocity, and they would leave the solar system. Do you have a question? No. Okay. So this is troubling, and this, we started seeing ice giants all over the place when we looked out, starting in the early 2000s, out into the galaxy, and it seems like they're very common. So this model doesn't work because obviously the ice giants are not leaving their orbits, and they are stable. So people started looking at new ways of what could be happening, and they started looking at the ways that the disk itself could generate local instabilities. There could just be points that were clumpier than others, and that these regions would then lead to nucleation closer to the sun, and then the gas giant, or the Neptunes, and the Uranuses, the icy bodies would form much in the same way that the gas giants would, except due to these gravitational instabilities, they would migrate outward. There would be different types of gaps in the disk, and we'll talk about these different migration schema in a second. So this seemed to make sense to some extent, and then there was this other idea that they started finding these icy giants actually quite close to suns, which was another predicament that happened in the last 10 years, which is a bit of a real nightmare at first. And that really changed the way people started thinking about the rocky planets too, because we realized that the evaporative flux of these stars was so great that these little Neptunes were going to turn into something rocky rather quickly. And this idea, once you have that idea, then you have to put it in phase with all of your other ideas about the solar system too. And this is going to take some catch-up work, and so we're still playing out the details of how that works. And we'll talk about that momentarily with this next paper. But the idea that these, it's a really tantalizing idea that the rocky planets could have had a moment in their past where they were closer to a Neptune or something like that, because it saves us from some of the crises about where all of our water came from. It plays in, interestingly, into even our tectonic situation, which I touched on a little bit with this expansion idea of the Earth, which is, has gone through a number of iterations. But the idea that we could have spent some time as a Neptune is to me a really exciting idea in terms of explaining what we see on our planet itself. The story of where all of our water came from when I was in college was that we got hit with a bunch of comets. But the first time I heard that, I really cringed a little bit, because the amount of comets that it would take to fill up oceans on Earth just seemed preposterous to me. It's hard to imagine, and we don't see anything like that when we look out into the sky. We don't see huge barrages of comets filling up planets. And so this is a troubling idea to me, and I think it was a troubling idea to a lot of people. So this idea of photoevaporation opens up a whole new door to why these planets look the way they do, particularly our planet, which is very strange and unique in our solar system, but it doesn't seem to be unique in general. We're logging hundreds of planets that look like Earth out there. They're finding more and more of our type of situation, which are these watery, rocky worlds. It's very strange. And we don't see hundreds of bombardment phases, right, where they're getting splashed with water. So this is really cool. Now, this is this paper that I came across yesterday, which is trying to work off of this idea, this migratory model of icy planet formation, and how it would transition to an Earth-like world, because there's a real problem with that, with what we see, which is that you don't see Earth-like worlds that are, well, you do see some of them, but for the most part, you see Earth-like worlds that are in two size compartments. There's a small group, and there's a large group, and there's nobody in between. And I think for really up to this very moment, people have been allergic to the idea that the rocky planets or the Earth-like planets were definitely spending time as Neptunes, because if that were the case, it's thought that there should be a perfect continuum of size distribution. You should see, if they were just photoevaporating Neptunes, or icy, they call them Neptunes, but they're just icy bodies. If that was happening, you would see a very nice range of size distribution. And so this paper was trying to address that. So just to be clear, there's this bimodal distribution, which you can see up here. And the idea is that you have two bins, right? One's about 2.4 times the radius of the Earth on one side, and one is below 1.4 Earths on the left side. And of course, there's some in the middle and so forth, but for the most part, they fall into these two bins. So what could possibly cause that? And, the authors started to model in how collisions between these worlds could essentially result in this bimodal distribution. So without completely boring you with the details of it, the idea is that as these mini Neptunes formed and perhaps made their way closer to the sun, or maybe they started even close to the sun, that they were crashing into one another. And that essentially the mid-range bodies all smashed into each other and became one of the larger bodies, or some of them didn't crash into anybody and they were the small bodies. So the gap in the size range was a result of these collisions. And it turns out, and what the paper argues, is that this actually helps us explain why they don't have bigger gaseous envelopes than they do as well. It helps us understand what happened to all of that atmosphere. And in my own reading of it, it also lends some interesting credence to the idea that the rocky bodies don't have these huge atmospheres as well. We don't have a huge atmosphere. You know, one of the biggest arguments against this expansion idea is that it would have taken too long to just lose our atmosphere piece by piece. However, if there was a couple of Earths in the beginning, well, not in the beginning, but in the early days of our solar system, they might have had huge atmospheres and they could have crashed into each other, especially following this model. And that's when they lost the majority of their atmosphere, was in like a discrete event. And it seems to be substantiated by the patterns of the size radius that we see out there when we look into the distance. Here's a couple of those migration models as well. The first type is this migration where certain gravitational instabilities, the Neptune forms, or the gas giant forms out in the reaches, and the gravitational instabilities lead to this like more elliptic rotation, which causes it to migrate inward. And in the type 2, it's a little bit different. In this case, there's actually this gap that opens up as it's orbiting. Material actually comes into the gap, the little gap envelope, and pulls it out of its orbit a little bit, which leads to it slowly working its way inward. In the third type, you actually end up with these vortices forming, which through its own torque in this material, where it's actually spraying material outward, which pulls it forward and it winds its way interiorly. But these are all different types of gas-driven migration, so they all depend upon the gaseous envelope, all of this rarefied material in the protoplanetary disk interacting with the planet through different gravitational means and yanking it inward. So, as these planets are migrating inward, and there may have been a lot more of them in the early solar system, they tend to resonate with one another gravitationally, right? As one goes around, it pulls the other, and they end up in these really beautiful clockwork situations where they orbit like 1-to-1 or 2-to-1 or any other harmonic overtone, right? And these play out in terms of the musical scale really nicely, which is it was quite an obsession of the early astronomers. And so as these resonances develop, they lead to more stable orbits. And this is thought to be the reason that our solar system has more or less been the way it's been for such a long time, despite the fact that all of our orbits are this really delicate balance between inward pull and outward motion. Yeah.
So all the migration models so far have been the icy giants moving inward. Is there any that suggest that they move outward?
Well, the problem with them moving outward is that they would leave, essentially. However, yes, to some extent, they can have drifted inward and then moved back out to where they were. It's tricky because, again, they're icy. So how did a big ball of ice form next to a really hot burning ball of something? That's the trick. And so nobody can really pull that off without forming them farther away and moving them inward at some point. And then, of course, they don't live inward at this point, and so the idea is maybe they move back out, especially depending on how these resonances snapped up, you know. And you know, it also has to do with the motion of Jupiter. Jupiter's thought right now to have formed somewhat similar to in place to where it is right now, but it may have drifted a little bit and yanked the bodies if it snapped into a new orbit, then it would perhaps drag somebody out. And yeah, I mean, these are all their best guesses, you know. It's these things that happened billions of years ago are very difficult to say with any certainty, which I think is actually really exciting. So I think the interesting thing that's brought in by this paper is just that giant scale impacts of bodies could really change the way that planets look. They could really take something from looking like a gas giant to looking closer to a Saturn or a Neptune even, which if it moved outward would then be capable of freezing and taking on that appearance as well. So there's a lot more degrees of freedom in the way that we theorize about the origins of these planets, the more that we learn and the more that we see planets being photoevaporated next to their star. I mean, it's hard to overstate how much of a shakeup this was when it happened maybe 5 or 10 years ago. I mean, 5 or 10 years, like really recently, people started to see these things happening all over the place, and they were like, what? What is a Neptune doing next to a star? Because this was complete violation of how we had thought about the formation of these icy giants in the past. And you know, generally it takes 50 years to really dial in a theory once you have the idea for it. So I think that's what's happening right now. And I think even next year when I teach this class, we'll have a lot more to say about it and every year after. So it's something to keep an eye on. But it does seem like there was more, it seems like there was more room for catastrophe in these early moments. And that these bodies may potentially exist on an evolutionary timeline, which is like really fascinating. You know, when you think about the theory of evolution, it's kind of taken as a foregone conclusion at this point. You know, you walk into an intro bio class, it's like, you know, well, the organisms evolved from, you know, something like we came from like these mammalian creatures that survived the dinosaur collapse and sort of like taken for granted. But that was not a popular idea when it came out. There was a huge scholastic camp that was like, no, humans, and every species for that matter, was formed in its own way, much the way we treat the bodies in the solar system, or have historically treated the bodies in the solar system, this uniformitarian concept. And they all sort of, maybe there was some slight changes along the way, but they were more or less formed as we see them. And this was the predominant view for thousands of years, and really even for a good 100 years, maybe less than that, but for a while after evolution was starting to be entertained, there was still a very stodgy camp in the academic world that wasn't interested in that idea. And so yeah, the idea of planets and suns being all on this evolutionary timeline together is a really fascinating idea. I mean, you know, we're getting comfortable with calling the gas giants failed stars, but that's a pretty huge leap, you know. If the timelines, like I say, if the timelines of the universe itself expand, you might see the evolutionary timeline going the other way even, where instead of being thought of as failed stars, maybe they're dead stars, right? I mean, we know that one of the endpoints for a star, of course, often they go nova and they blow up, and there's all sorts of different things that can happen. But one of the things that can happen is something called a black dwarf, which is formed, which is basically a cold, dead core of a star, right? And the cold, dead core of the star turns out to look a lot like a big ball of metal, not so different than the cores of a lot of these things, right? Again, that would take trillions of years to make one of these black dwarfs, at least hundreds of billions of years, longer than what cosmologists believe to be the age of the universe. But it's so fascinating because you can see how just in the 1960s, people were entertaining the idea that the universe had no beginning. If the universe had no beginning, that would be a completely reasonable conclusion for a new point on the evolutionary timeline of these planets, right? And so our ideas are constrained largely by our cosmology as well, which is really just fascinating to me. So at any rate, there do appear to be evolutionary processes, and the planets do seem like they can, there is evidence that they could transition between one type and the other, especially with regard to these icy planets and the rocky planets, which is, I just think it's one of the most exciting things in all of planetary science right now. It's really at the edge of where we are, and it has interesting parallels to the history of science in general with evolutionary theory, and it's really something to think about. So yeah, so collisions may have played a big part in why we don't see more Earths, and why we don't see in our own solar system, and why we don't see these particular size, this gap size of Earths when we look out into the galaxy in general. Cool. Do I want to say anything else about that? No, I think that's good. And so the authors go on. They actually go one step further, and they actually say that, if we had these collision events alone, that we wouldn't end up with a proper composition for a lot of these protoplanetary rocky planets. But if you actually factor in another step of photoevaporation, where after these collisions, these small bodies then also evolve in the present, being very close to the sun, evolve, then you can end up with something that looks a lot more like our Neptune or our Uranus. So, and I think that's really important too as a mode of theorizing, is to never be so tunnel visioned about your ideas that you don't think about how the other theoretical ideas could play into the model in general. It's very important to be integrative when you're theorizing. And this is one of the biggest tragedies that you see when you go, I talk to people all the time who have theories about how things work, and they're often controversial theories. And one of the saddest things that I see all the time is that theorists have a really hard time saying, well, my idea is a good idea, but you have a good idea too. Maybe our good ideas can work together. This is, even in standard academia, this is a really, really hard thing for people to do. They want their idea to be at the exclusion of all other ideas. And I think that's a real mistake to make as a scientist, because oftentimes the theories that we hear about aren't necessarily the best ideas, but they're the ones who are made by the people who could play well with others. There's an undeniable human quality to doing science. Nobody does it in a vacuum. Einstein's probably our most famous scientist that everyone knows the name of. But Einstein had a huge network of people that were propping him up when he was doing all of his famous relativity work. I mean, his buddy Minkowski did almost all of the mathematics for his theory, and nobody really gets that. And it's kind of a tragedy, because people in our culture right now think of, we want heroes, we want individual people who have done all this work, who get prizes for their heroic efforts. But in reality, these things happen through rich collaboration, and no one person can have all the knowledge necessary to assemble all the pieces of a puzzle this big. So if you go out there, you end up being a scientist, do not neglect collaboration. It is absolutely essential to your success, to people listening to you. Because you might have the best idea in the world, but if no one listens to you, it's going to be a sad life. I promise you that. Okay, so let's talk about our ice giants a bit. Here they are. Uranus is a rather featureless planet, which was quite startling when we made our first approaches. These are photos taken from some of the approaches, and we'll talk about those missions a little bit. The idea, this concept of ice is a little misleading too, by the way, and we'll unpack that a bit later. But when we say ices, we actually just mean volatile compounds that have freezing points above 100 K. So this is water, ammonia, methane, things like this. The trouble is that much like the gas giants don't actually exist in a gaseous form because the pressure is so great, similarly, in these bodies, the volatile compounds that would normally form ices if they were atomized, if they were just in a vapor form, they're under extraordinary pressures. And the pressures at which water is one of those incredible molecules. It is the most incredible molecule in the universe, for sure. And it does very, very bizarre things under different pressure conditions. And in our case, when we start to think about what causes the magnetic field, these guys have huge magnetic fields, by the way. Not quite as big as Jupiter, but much bigger than the Earth. And so they don't, without that liquid metal layer, scientists have been scratching their heads about how they pull this off. And it almost certainly has to do with some strange form of water that's existing at subsurface layers in these great pressures where dissolved, where it actually acts like an ion, like a metal. It actually ionizes in a way so that the hydrogens are dissociated from the oxygens, and you can actually get little current sheets going inside of the ice itself. I mean, and this is, the pressures that are involved here are astronomical. It's nothing like what we can make on Earth. So these are largely untestable hypotheses. But again, we know there's a magnetic field there. So, and we know there's no metallic hydrogen. So how's it happening? We'll explore that in a little bit in greater depth. So, until the 1990s when we actually went out there, robots, we didn't treat the ice giants as a separate class from the gas giants. We were just like, it's basically the same. So guys, 1990s, right? This is like when I was in high school. This is, middle school. This is really, really recent. The change in the way that we see these things is just completely at breakneck pace, even right now. So there they are. Let's get a good view of these. So the two we're going to be talking about, Uranus out there, and here she comes off the edge, right? They're very far away. It's hard to get a sense of scale here, but they're the furthest planets that we have. Pluto's out there too, but Pluto's been demoted recently on account of the fact that there's a lot of Pluto-type bodies, and so we're going to draw the line arbitrarily. But they're our biggest planets, and they go really slowly around their orbits. Here's a more stable view of that. So generally, beyond these two planets, we have what we call the Keplerian belt, which is just this sea of other orbits, which are these small bodies, these trans-Neptune objects like Pluto, like others. That I think there was a different one shown actually on the previous slide, but there's hundreds of these bodies. In terms of the composition, the main distinguishing feature, and I'm going to ask you guys next time, so somebody remember this. If you're going to remember one thing, the icy bodies have more complex, heavier molecules, elements and molecules than the gas giants. The gas giants are very simple. They're hydrogen, they're helium. These are really basic. Those are the most, like hydrogen is a single-shelled atom. It is a spherical, simple atom. These ice giants, on the other hand, are largely these volatile chemicals which are molecular in nature. And perhaps they exist, like I said, in strange forms where you don't have molecular water. It's actually been ripped apart and it's forming these different layers and conductive bands and all sorts of structures that we can hardly grasp. But they're more complex, right? And so from an evolutionary standpoint, I think that it's reasonable to speculate that the complexity means that these planets are perhaps downstream even, right? So maybe the early Neptunian objects were closer to gas giant looking things with more simple elements originally, and then as they migrated and found themselves in situations where they could condense molecules, then that's when they formed these the bulk of their bodies. So maybe their cores were formed in something more similar to a Jupiter-like process, but their actual bodies, these icy bodies, formed in a later evolutionary process. There's something else I wanted to say about that. It's escaping me. So we talked about how they never really, they do have some hydrogen in their envelope, but it never penetrates to the depths that we would get that metallic version. Still, the envelopes, they're very thick. It makes it very difficult for us to see deep into their interior, much like the gas giants. So everything that we're coming up with about their interior is largely the result of what we understand about chemistry and pressure dynamics with respect to the observables, which is essentially their density. We can see their radius, we can gauge their mass from their orbital dynamics. But in terms of making sense about what's happening on the interior, we're really theoretically limited there. We can't produce those kinds of environments on Earth, and so we're extrapolating curves into the distance on these phase diagrams for what it might be like down inside of them, right? And this means that we'll probably change our minds a lot as we learn more and as we send probes into them. One of the things we do in science all the time, which is a fantastic ability, but also leads us up trees sometimes, is that we'll come up with a formula for, let's say, how an ice behaves at this pressure on Earth, and then we'll raise the pressure and it behaves a little differently. And so we'll come up with these curves of how things are expected to behave indefinitely. The problem is nature has all of these strange biostability points and these strange equilibrium breaking moments where things will just change suddenly all of a sudden, you know? Instead of having an ice like we have on Earth, all of a sudden your ice is perfectly conductive. It's acting like a metal, you know, under these extraordinary pressures. Things like this that we can't possibly conceive of, but we know there must be something like that happening because of the macro phenomenon that we see, like the magnetic field. So we're going to learn a lot, but basic structure compared to our gas giants over here is some sort of a core, which we don't totally know whether it's an icy core or a rocky core. We have a mantle, which is basically water, ammonia, and methane ices. And then there's a little bit of an envelope there with hydrogen and helium, much like the gas giants. So these bodies don't have solid surfaces. I believe I mentioned that already, but there's no real way to put a point where the planet begins and where it ends, which is really interesting and tricky. We actually nominally refer to the edge of the planet as the point where it has the same surface pressure as Earth, 1 bar of pressure, which is quite interesting, which is actually quite far out from even the liquid levels. What else can we say? All right, so they're very strange too, right? So I mentioned they have strong magnetic fields. This is true, but the magnetic fields are offset in a very peculiar way, which again opens up our minds to the idea that something else must be happening than what we're used to on Earth. So, you know, look at these, their spin tilts are set off from their magnetic axes by, 45 more degrees. So what's going on there? The thought is that they have these very turbulent supercritical layers, which are somewhat uncoupled from the actual rotation of the planet. So when we think about our own magnetic field on Earth, we think about the generation of those eddies as being a product of both some sort of convection, but also as a product of the Coriolis forces, which are the same forces that give us that pendulum and give us the patterns of the swirling of hurricanes, right? The Earth itself, as it rotates, is going to offset any forward momentum. And so we tend to think about our own magnetic field as being a product of those two forces, but it doesn't totally make sense in the same sense for these icy bodies. And so there must be something else going on there. And, this is a very difficult lecture to give for me because what we know about these planets is so little, actually. I just read a bulletin from the Royal Society yesterday that was essentially a cry for help that, hey, we got to get some more spaceships up there because we know almost nothing about these icy giants, actually, particularly how these magnetic fields work. And I think that understanding how magnetic fields are generated is absolutely pivotal to our success exploring space in the future. If we can find a way to bring planets into more stable magnetic fields, maybe there's ways to do that with ionized water even, right? Maybe we can do it for our own spacecraft, because traveling from here to Mars is a very dangerous enterprise. There's solar wind and cosmic rays and things that will absolutely shred your DNA. And it's not totally clear, despite all of the enthusiasm, how we're going to handle that. So I think understanding the generation and the idea that Mars, that we can even terraform it in the first place, depends on the idea that we can reinstate a magnetic field there. So there's a lot of reasons to get out there and understand what's going on, but unfortunately, it's not very well understood right now, other than the fact that it's weird and that these superionic, supercritical fluid ices must have something to do with it. So this is really cool. By the way, those ices are very hot as well, too, which is another idea that's completely at odds with the way that we think about ice. Ice really just means a solid form of something that's generally volatile. So in this case, you have, I wouldn't want to call it a metal, but it's actually closer to a metal than what you would think of as like a fluid or like an ice that we'd see on Earth, right? It's a very, very strange proposal, but I think that it's valid, and I think that water, if anything could do it, it would be water. Water can do incredible feats under different constraints. And they keep trying to make these hot superionic ices in the lab, and they're coming up with all sorts of contradictory results. Different groups come up with different findings, and it's a very difficult process to replicate. But the best of our knowledge, they are generated in these thin fluid layers that are actually relatively shallow, closer to the surface. And that's the best we're going to get today for the magnetic fields of these bodies. Okay, so last part of the class, we're going to talk about the two of them and compare and contrast them a little bit. So we'll start with Uranus, since it's the closer one. It's the 7th planet from the sun, and it actually has the 3rd largest planetary radius, but the 4th largest mass in the solar system. So Uranus is actually visible to the naked eye. I have not seen it myself, but I'm told that it's visible. And apparently the ancients were somewhat well aware of it, although because it moves so slowly in its orbit, everyone thought it was a fixed star for the most part. And they figured when they couldn't see it that it was just obscured by weather or something like that. And so its formal discovery wasn't made until much, much later. And it's actually an interesting process. We talked about it briefly when we were doing all of the Keplerian dynamics with with gravitation and all of that, because it was it's heralded as this triumph of mathematical physics, because its location and its presence were predicted before it was formally observed. Let's see. Uranus, it's actually named, again, from our Greek tradition, which is actually a Romanized version of the Greek god Uranus, which is, the Greek god Caelus. The Romanization is Uranus, which is part of the myth of Saturn, which is pretty crazy because in that myth, Uranus, or Caelus, castrates his father, which is Saturn, and then throws the pieces, dismembered pieces, into the water, which forms Venus. And this is a really gruesome myth if you think about it. And you try to think, like, why did they come up with this story? I think that it, one argument is that it has to do, Cronus, this idea of time and order, I think is central to the idea because you actually have this severing off of chaos from order, and you're actually starting to create a myth of how predictable regularity appears in the world. Did you have no? I keep thinking you have a question. Sorry. Oh, no worries. Uranus gets different names in other cultures. In the East, in China, Japan, Korea, and Vietnam, it translates to Sky King star. Where else? I couldn't find indigenous records of this story, and I think that's because it's a very difficult star to see. Again, Mongolian king of the sky. But anyways, it wasn't really seriously considered until Herschel observed it in 1781. And this, of course, followed a very long discussion of its mathematical presence, how it should be there. Now, sorry, I'm getting Neptune mixed up with it. Neptune is the one that was deduced mathematically. So we have been out to it a few times. In 1986, we sent Voyager 2 out there. And Voyager 2's flyby is still the only mission that was carried out with really short range and no other visits. Voyager 1 tried to go to Uranus, but decided to hang around Titan instead because they were getting so much interesting information there. And you can see the path of these orbiters here. This is just Voyager 2. So Voyager 2 was launched in 1977, and it made its closest pass in 1986, which is basically through the cloud tops. Actually, not even that close, but it was about 81,000 kilometers above the cloud tops, which is pretty cool. Voyager 2 then went on to check out, we'll get to that in a second. We sent Cassini back recently, which was, I believe, in the early 2000s. Cassini went to Saturn. They were planning on sending Cassini out to Uranus as well, but they basically decided that it would be cooler to crash it into the atmosphere and get more information back from Saturn instead. So it didn't do that. So we have very, very little close-up data on this planet. Which is, again, I think why the different scientific communities are begging for another mission to go out there so that we can learn something more, maybe actually crash something down into its atmosphere and get a little more information on how these ices are arranged. Uranus orbits once every 84 years, which is a long time. It also has it has the most eccentric orbit of any planet. Pluto is actually more eccentric, but Pluto, like we said, has been cast out of the planet party for somewhat arbitrary reasons. But the difference between its maximum and minimum orbit is actually 1.8 times the distance of the Earth to the Sun. So that's a pretty highly elliptical orbit. And as a result of it, there's a lot of changes seasonally, right? So it doesn't get much light. It actually gets about a 400th of the intensity of light that we get on Earth here. So it's possible that the different changes that we see actually have less to do with the light and more to do with things that are happening internally as a result of the tidal sloshing as it moves in this highly eccentric orbit. It rotates pretty fast, 17 hours, 14 minutes. And it's at a pretty bizarre axial tilt. It's actually tilted at 97.77 degrees with respect to the plane, the ecliptic plane. And we define that as prograde, which is forward rotation, but this is somewhat arbitrary since it's so bizarrely offset. So near when it's at its solstice, one pole faces the sun continuously and the other faces away. So these seasons are really extreme. So each pole gets about 42 years of continuous sunlight and then 42 years of darkness, which is really interesting. One thing that's quite strange, though, is that despite this, it remains hotter at its equator than at its poles, despite the fact that one of them is getting continuous sunlight all of the time, which means there's some other processes going on there in terms of dictate. Like, again, there's something else happening with regard to the weather patterns within it. But that's a big mystery, actually. The mechanism that causes that equator to stay hotter than the poles, despite their exposure, is not known right now. That's a good project for somebody to investigate. There it is. I thought it would be interesting to show the Earth next to it. It's about 14.5 times the mass of the Earth, but it's actually only about 4 radii. And so that results in a pretty low density. It's actually the second least dense planet right after Saturn. What else should we say about this? Maybe I was going to go into more depth about its composition, but I think in the interest of time, so we can make it to Neptune, we'll just keep cruising. Uranus has a very strange internal heat situation. It's very cold, actually much colder than Neptune, which is very strange. Neptune actually gives off 2.61 times as much heat radiation as it receives from the sun, but this is not the case for Uranus. And so that difference is very, very poorly understood, and it's something to consider. One idea is that if one of these giant impactor events happen, like we spoke about at the beginning of class, that it would be possible for this to have actually dissipated a lot of the internal heat in the early days of its existence, which is cool. It's integrative, and it fits in with some of the other models that are popping up. Let's look at its atmosphere a little bit. It doesn't really have, like I said, it doesn't have a solid surface. So we talk about its outer envelope, this more volatile region as the atmosphere. Oops. So Voyager 2, when it went over there, it found that the southern hemisphere had a few different regions. It had this bright polar cap and these equatorial bands in the atmosphere. And there's a lot of speculation about what was causing those. It's thought that the methane itself is actually what's responsible for this bluish color, because methane absorbs in the visible and IR and basically leaves behind the colors that we see, this sort of aquamarine cyan color. We also see hydrocarbons up there in the atmosphere, which is quite interesting. You know, for many years, actually when I was a kid too, hydrocarbons were essentially thought of as originating exclusively from dead stuff, right? Coal or petroleum were always considered, they were actually called fossil fuels while I was growing up almost exclusively. We now, especially with the exploration in the 80s and 90s and 2000s, we began to realize that hydrocarbons were found elsewhere and that it wasn't likely they were coming from dinosaurs on Uranus. And so these complex organic molecules having some sort of other synthesis pathway really took over in the way that we think about those on Earth right now. And that's not to say that that some of the hydrocarbons on Earth don't come from dead stuff. They certainly do. But there's also other paths to it. And so that's a really interesting paradigm shift. People just sort of stopped calling them fossil fuels at some point in the last 10, 15 years. I think largely as a result of this exploration, which is pretty cool. All right. It's got some moons. We're going to deal with all of its moons next time. It's got 27 natural satellites. And the satellites are actually named after Shakespearean characters, which is quite different than the Greek mythologies that we're used to. We'll get into those more next time. It's also got a ring system, which we'll save for next time. All of these gas planets actually have ring systems. Neptune, somewhat similar. It's the 8th planet from the sun, farthest known planet, again, barring Pluto and all of the trans-Neptune objects. It's the 4th largest planet by diameter and the 3rd most massive planet. So it's actually the densest gas giant, which is interesting. 17 times the mass of the Earth. It's bigger than Uranus, and it's denser and smaller. Right? By radius, it's smaller than Uranus, actually. But it has, this is just due to the gravitational compression of its atmosphere. Named for the Roman god of the sea. This is actually the one I think I had this confused, but again, Neptune, it's not visible to the naked eye. Galileo seems to have made some observations of it, although he didn't seem to realize what he was observing, so he's not credited with its discovery. And this led to a whole downstream chain of events about who gets credit for discovering Neptune. This was the one, I misspoke earlier, but this was the one for which the mathematical physicists herald as a triumph of calculating ability because they predicted its location before they actually went out and found it. So we'll save that story for another day. Let's see. Voyager 2 visited Neptune right after Uranus. And this close approach happens in the summer of '89. It went and checked out some of the moons as well. Let's see here. What's interesting is that if we ever go out there and explore things, it's going to take a while to communicate with those robots. It took 246 minutes for a signal to reach back to Earth, which is a real trick in terms of driving a robot around out there because, you push go forward and it takes a few hours. And people are trying to come up with interesting ways of, maybe we'll actually we'll have stationary orbits around these planets so that there can actually be people there to control the robots that go down and explore the deeper levels. China's working on a spacecraft to get out there. They're calling it Interstellar Express. Right now, NASA's not really planning anything like that. They're like, maybe we'll deal with it in the 2030s. There's nothing totally on deck. There's a concept mission called Neptune Odyssey, but there's nothing really built for that. And it's expected that even if they did get it out there in the 2030s, it wouldn't be out there until like 2050. We've already talked about its orbits. Also, Neptune is also tilted pretty wildly. So it's at well, no, that's not true. I take that back. It's actually quite similar to Earth. It's 28.32 degrees. This is different than Uranus. Remember, Earth is tilted at 23 degrees. Mars is about 25 degrees. So it has similar seasonal changes to Earth. There's none of this extreme polar exposure and so forth. Neptune also orbits very slowly. Let's see. Each season lasts for about 40 years. And its rotational period, its day, is about comparable to Uranus. It's 16 hours long. Composition-wise, Neptune, very similar situation. Probably not even worth discussing the differences in. Atmosphere, also very similar. Hydrogen, helium, atmosphere, very similar to a gas giant. And, you know, one thing that we did see on these flybys is that there's some pretty phenomenal storm systems going on. I'll leave those to you. Your textbook talks about them a fair amount. And yeah, I suppose we're out of time, but I guess the closing remark is that there's not a ton to say about Neptune that's different than Uranus. And quite honestly, we know very, very little about these planets. And so maybe you guys, your generation, will fill in the gaps for us in the future. Have a good weekend, guys, and we will do it all again next week. We will get into the moons of these planets. We'll talk about the ring systems. It'll be good.